Alright, today will be a combination of two videos. I have a full lecture recorded, but for some reason the first couple of slides from chapter 16 and 17 are missing. So the first thing you need to know, we're going to have, we combine chapter 16 and 17 for the next exam. So there really is only 2 or 3 exams left in AP, so make sure that you buckle down and do well on all of them because they're going to be very important to your grade. So let's go ahead and just dive in. We're talking about acids and bases. So the first slide, just some definitions of acids and bases. There's multiple ways to define something as an acid or base. The first one we'll talk about is an Arrhenius acid or base. So the definition according to Arrhenius of an acid is a substance that when dissolved in water increases the concentration of hydrogen ions. A base is a substance that when dissolved in water increases the concentration of hydroxide ions. So the typical acid we've been using is HCl. If I add it to water, let's say plus HOH, it's not really a reaction, it's just a dissolution. When I add it to water, the H plus and the Cl break up. We're going to learn that HCl is a strong acid, which means that when you add it to something, it will completely dissociate. Now, we actually learned that chapters and chapters ago, but it's pretty easy to see this definition now of a substance that when dissolved in water increases the concentration of hydrogen ions. So H plus, we've added it straight in. Now remember, water itself is a balance of HOH together going to or coming from H plus plus OH minus. And when it's neutral, these things equal each other, the H plus and the OH minus. But when I add HCl, the amount of H plus will go up. Alright, so we would call HCl an acid because it increases the concentration of hydrogen ions. Now the exact opposite is true for a base. We still have water, and it still is in equilibrium with H plus and OH minus, but this time I'm adding a strong base like lithium hydroxide. That completely would break apart, so the concentration of hydroxide would go up. So we would define lithium hydroxide as an Arrhenius base because hydroxide is increasing. Pretty simple. Alright? So a Bronsted Lowry definition of an acid is a proton donor. Let's erase it. So HCl decomposes or dissociates really into H plus plus Cl minus. H plus is really a hydrogen atom that has lost its electron. So a hydrogen atom is a proton surrounded by an electron. But if it becomes positively charged, it means it lost its electron. And so really it's just a proton. So HCl can be defined as an acid according to Bronsted by definition of its donating a proton to something. And then a base is a proton acceptor. And so if you have like LiOH, when it dissociates or dissolves, you have Li plus plus OH minus. All right, if you have a solution and you have OH minus in there, it will be looking for an H plus to stick to it, or it will accept a proton. So those are those two definitions. Bronsted Lowry is the proton donor and acceptor, and the Arrhenius definition of increasing H plus or OH minus. All right. There we go. A Bronsted Lowry acid must have a removable or acidic proton. That's why they typically start with H. They don't have to, though. You could have NH4. If I drew this equation this way, NH4 could give off one of the H's to produce this. And we'll learn about what's called conjugate acids and bases. But typically an acid will just start with an H and we'll give it off. A Bronsted Lowry base must have a pair of non-bonding electrons. That's a little bit of a different definition that we don't use as much, but something like NH3 here. So NH3 was here. It had its non-bonding pair right there, and it attracted the hydrogen ion to that and stuck to it. So that's why the proton would stick to the non-bonding pair. If you want to write those in your notes, you go ahead and pause it if you need to. And we'll move on. So if it can be either, it will be called amphiprotic, and then the rest of the video will pick this up, or the different video.